Hey guys, welcome to the Polarity lecture and notes. We're going to get started pretty much right away here. So for this assignment, like the previous assignment where we took some notes while I gave a lecture, you're going to need to either get out your own piece of paper to write them down in the Cornell Notes style, like we did on the previous notes, or you can open up the other document that is attached to this assignment on Google Classroom. That document, again, has the setup with the left side is where you're going to write the cues, which are the titles of the slides. And if you have any questions during the lecture, you can put that below on that left column. And in the right column, you're going to put notes, definitions, and pictures. To help you out, after each slide that I lecture on, I'm going to have a slide where we'll pause and you'll copy down what is on that slide in this format right here to help make it easier for you. So let's start with remembering different types of bonding. So you just finished an ed puzzle reviewing covalent bonding, but really quickly, let's remember ionic bonding. So in ionic compounds, you have a transfer of electrons forming ions. Because those electrons are negatively charged, if they're moved from one atom to another, that means that ions or charged atoms are going to be formed. They always occur between a metal and a nonmetal, and it's when the electronegativity difference between those atoms are greater than 1.7. So this example here of calcium and chlorine, to fulfill that octet, remember octet is that 8 that they're shooting for, the calcium, which has a smaller electronegativity than the chlorine pulls those electrons from the calcium, and what has resulted are calcium +2 ion and 2 chlorine -1 ions. So here's what you should have written down for this. Now, covalent compounds, again, you should have just done this ed puzzle to help to remind you about what that is. A covalent compound is when you have electrons not being transferred or moved, but just being shared between the atoms. No ions are formed, therefore, because no negative electrons are being moved, and it's always going to be between nonmetals. The electronegativity difference is less than 1.6. So when we studied this previously, that was kind of just the cutoff we were looking for. Bigger than 1.7, it's ionic. Less than 1.6, it's covalent. So this example here, I believe these are two oxygen atoms. Each share a pair of electrons, or no, this isn't oxygen. This has to be a chlorine or a fluorine. But nevertheless, a pair of electrons are being shared. So they both get to use them to get to that octet without having to give up or take any electrons away. So here's what you need to have written down for that slide. So when we talked about covalent molecules the last time, we really just focused on the fact that the electrons are being shared, and the electronegativity difference is not enough that electrons are actually being moved. But if you remember, we actually had two different classifications for covalent compounds. You had what are called polar covalent compounds or non-polar covalent compounds. So polar covalent compounds occur between when the electronegativity difference between the atoms is between 1.7 and 3. And nonpolar is when the electronegativity difference is less than 0.3. So the electronegativity difference isn't that great. So when we talk about bond polarity, what we're saying is that electrons actually aren't always equally shared. So that means that one atom, although it is not strong enough to fully pull the electrons off of another atom, they tend to pull the electrons towards themselves a bit. So if we use hydrochloric acid or hydrogen chloride, HCl, as this example, let's take a look. So if chlorine has an electronegativity of 3.2 and hydrogen has an electronegativity of 2.2, that difference is not big enough for the chlorine to fully pull the electrons all the way off. They're still going to be shared. However, what we're going to see is that the chlorine actually is a little greedy and is pulling electrons further towards itself. So here's what you should write down for that slide. Now, what results when those electrons are being pulled ever so slightly towards one of the atoms is a partial charge. So in this case with the hydrogen chlorine, the chlorine is pulling the electrons a little bit further towards its side. And remember, electrons are negatively charged. So if they're pulled further towards the chlorine side, that means that the chlorine side is actually going to have a partial negative. And we signify it with this funny, like kind of S, like almost infinity sign, meaning that literally just means partial. So here's what you need to write for that slide. What that means then is for the hydrogen is if its electron is being pulled towards the chlorine a little bit, or is being pulled more in that direction, just like in an ionic bond where the thing that loses its electron becomes positively charged, the hydrogen is actually going to have what we call a partial positive because the electrons are being pulled away from it towards the other atom. Again, that funky little partial sign with a positive signifies a partial positive. So here's what you write for that. So that is showing a polar bond. But when you have electrons that are being unequally shared between two atoms, not so much that it's an ionic bond, but enough that there's these partial positives and partial negatives, that is a polar molecule. So it's a larger difference in electronegativity compared to a nonpolar bond where the electrons are pretty much equally shared between the two atoms. But again, it's not a big enough electronegativity difference where the electrons are fully pulled off. So here's what you should write for that. And this image over here is showing what a molecule that is polar it looks like, or a bond that is polar will look like, because the electrons are being pulled ever so slightly towards that chlorine side, giving it a partial negative, resulting with the other atom, in this case a hydrogen, having a partial positive. So write that down now. Okay. Now, when we said that the electronegativities are similar to each other, recalling that chart that I showed at the beginning, if the electronegativities aren't that different from each other, the electrons are essentially just being equally shared. And that's usually between either a molecule or a bond where there's the same atoms are bonded to each other because they have the same electronegativity, so neither one is stronger than the other, or just when you have two atoms with like electronegativities. So here's what you need to write for that one. For this case, hydrogen is a really good example of that. The two hydrogen atoms are going to form H2, where they're going to share their electrons to get to what they want is a full 2 because it only has one shell. But neither is pulling the electrons further towards one side or the other because they have the same electronegativity strength. So that means that they have an equal sharing, and that's what a nonpolar molecule is. So write those notes now. So we're not going to get into this, but this idea is that there is a dipole. There is a pole of electrons in one direction. And in a polar molecule, you have a dipole. You have electrons being pulled more in one direction than the other. In a nonpolar molecule, the electrons aren't being pulled. They're equally being shared, and there's no partial positive or partial negative here. So the easiest way to see if a molecule is polar or nonpolar is to look at its symmetry. So this is a math concept, but the idea of symmetry is if you can cut something in half in multiple directions, it's symmetrical. If you can cut it in maybe one direction, it might be symmetrical in one way, but not in another. Or it just may not be symmetrical at all. So the thing that you need to know is that if you see a symmetry, if a molecule looks the same on both sides, that means that the molecule is going to be nonpolar. So if the molecule is perfectly symmetrical, you recognize it is a nonpolar molecule. If it is not symmetrical, meaning if there is an imbalance in some way, if it is not the same on both sides, then it is a polar molecule. So write these notes now. So looking at our examples before where we saw the hydrogen and fluorine, where this dipole, there's being a pole of electrons, if you cut or put a line down the middle to signify this, to look for this symmetry, you notice that the left and the right are not the same. Very clearly, there's a hydrogen and a fluorine. They are not the same, so it is not symmetrical, which means that it is polar. Now with the fluorine, F2 NH2 molecule over here, it is the same on both sides. It is symmetrical, and that signifies that this is a nonpolar molecule. So you can pretty much determine if it's polar or nonpolar without having to go through all the trouble of looking at the electronegativity differences, just by looking to see if there is symmetry or not. Okay, so here are a couple other examples for you. If we put a line through the middle of this molecule here, up and down, it does appear to have some symmetry. But if I go across the middle this direction, it is not symmetrical. So this NH3 molecule is actually a polar molecule. It is not symmetrical, therefore it is polar. The bromine, however, again, if I cut a line this way, if I cut a line this way, if I'm looking for these lines of symmetry, it is the same on both sides because it is the same atoms on both sides of the molecule. Therefore, this would be an example of a nonpolar molecule. So, the next activity is a short Google form where you're going to be checking for understanding of being able to identify if if molecules are polar or nonpolar based on symmetry. That's where you'll go next for the second piece of this. This is important because we're going to then focus on talking about how water, H2O, is a polar molecule, and that is really important in all of the behaviors and properties of water that make it such a miraculous molecule. So, good work, guys. I hope you have those notes written down. I hope you have either done them on your own piece of paper or you have done it in the document that I have attached. And make sure that you submit. You need to not only watch this Edpuzzle, this video, but you also need to make sure that you submit your notes. That's what I'm looking for. For the next step where you're doing this Google form, please use these notes. Please use the notes. Remember, everything that we do, you are allowed to use any of the work we've done before and any of the notes that we've been keeping to help you be successful. Great work this week, and I'll see you later, guys.